So first, I'm going to put up something for you to think about. So this is sort of like a challenge problem, or like a puzzle, maybe. Puzzle? So if we look at the linear transformations from Rn to Rm, right, that's actually a vector space. That's actually a vector space, right? Because you can add linear transformations together, right? If you have T and S that are both linear transformations, you can add them together, and that's still linear transformation, right? And you can define like the multiple of a linear transformation by just saying that take it to is going to be A times T of B. Okay. So in any case, I hope it sort of seems intuitive that linear transformations are also things that you can add together and then you can scale them. Okay, so that's a vector space. Now remember last time we said that every vector space is going to be isomorphic to some some Euclidean space, right? So here's the challenge puzzle. What Euclidean space do you think this is isomorphic to? Right? Like the polynomials of degree less than 3, those guys were pretty simply isomorphic to R3, right? What about the linear transformations from Rn into Rm? Anybody want to make a guess? No, there's no penalty for guessing. Okay.
Is it R like m by n matrices? Like R of m?
So is it going to be like R n by n?
Yeah.
Something like that? That is right. That's right. It's going to be the m by n matrices, right? So it's right. That in turn is isomorphic to m times n. So it's Rmn basically. But yeah, that's right. Should I give you points for that?
I think so.
Okay, I give you 2 points. 2 percentage points on the next exam, if I remember.
Okay.
That's the trouble. Who has points in this class? Okay, so other things that I want to recall. Most important at this point, that if you have 2 linear transformations from one vector space to another vector space, if the 2 linear transformations agree on a basis, then what happens? If they agree on the basis, you guys did this last class. If they agree on a basis, then they agree everywhere, right? So, right. So if TB1 equals SB1 for like I equals 1 to n, where the BI's are some basis, then TB equals SB for all B in your vector space, right? In other words, T and S are the same linear transformation, right? So to check if 2 linear transformations are identical, you just need to check that they behave identically on a basis. Okay, so that's just things to keep in mind. That's just something very important to keep in mind during during what we're talking about for this class. So, like I said, we're finally going to go into section 4.2. Okay, so. Okay, so section 4.2 is called matrix representations. Matrix representations of linear transformations. Okay, this is that idea that every linear transformation is can be associated with a matrix. Okay, and the first thing we're going to do is to consider linear transformations from Rn to Rm. Okay, so later on we'll do it for like the derivative, which is a linear transformation on some abstract vector space to some other abstract vector space. But right now we're just going to think about linear transformations going from Euclidean space to Euclidean space. Okay, so case of Rn to Rm. Okay, so let's recall that given any matrix given any n by n matrix, then we can construct a linear transformation out of it. Right? And we call that linear transformation T sub A. Right? How do we define T sub A? Somebody just tell me, what was T sub A? You have a matrix, we make a linear transformation out of it. The linear transformation does what? Anybody remember? Charlotte? No? It's okay. You twitched. Your hand twitched. But you had things. The linear transformation that you get by left multiplication. Remember that? Right? T sub A goes from Rn to Rm and takes a vector to A times the vector. In other words, T sub AB is AB. Okay. Sometimes we don't even distinguish. Sometimes, being sloppy, we just think of this thing as the linear transformation. We just say, oh yeah, this is the linear transformation. Really what we mean is the linear transformation is the thing that multiplies on the left by that matrix. Okay, so now going the opposite direction, so the converse. In fact, given any linear transformation, T going from Rn to Rm, there is a matrix A that that does the same thing, such that T is left multiplication by A. T is just left multiplication by A. Okay, so there is a matrix that will do exactly the same thing as that. Okay, so let me give you an example. So here we have a linear transformation, and what it does is it takes x1, x2, x3, and it gives you back x1, x1 plus x2, x1 plus x2 plus x3. Okay, and maybe you can guess what matrix will do exactly this. Can anybody just guess what the matrix? If we take A to be blah, then left multiplication by A is going to do the same thing as this. Sure.
Maybe.
Yeah.
So like 1, 0, 0, then 1, 1, 0,
Yes.
1, 1.
Yes, exactly. That'll do it, right? Because then when you multiply x1, x2, x3 by it, bam, you get x1, then you get x1 plus x2, x1 plus x2 plus x3. Right? right? So then T does the same thing as T sub A for this matrix A. Okay. Notice, what's T of 1, 0, 0? What's T of 1, 1, 0, 0? If we suppose we don't know this matrix thing, T of 1, 0, 0 is going to be what?
1, 1, 1.
1, 1, 1, right? What's T of 0, 1, 0? 0, 1, 1. And T of 0, 0, 1? 0, 0, 1, right? And you notice that those things are actually the columns of the associated matrix. Okay. That actually is not a coincidence. That's actually how you get the matrix. So. So let's write that down. Theorem. If T is a linear transformation from Rn to Rm, then there exists a matrix in R m cross n such that T is Ta. Proof. Let A be the matrix where the ith column of A is T of the standard basis element. Okay, so I don't remember if I said this or not, but these guys, E1 is 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0, 0, et cetera, et cetera. And those guys are called the standard basis. Okay, those guys are called the standard basis. So the way you get the matrix is you apply the linear transformation to the standard basis, and you get these you get the columns of the matrix that you're looking for. Rows, columns, okay, good. Okay. So I claim that T sub A of a vector is just going to be T of that vector. Okay. I claim that this A is going to work. That this is the A that's going to behave like our linear transformation. Okay. And notice that it suffices to show that that they agree on the standard basis. E1 to En. Right? It's that's because if they agree on this basis, then they agree everywhere. Right? Right. That's, remember, two linear transformations. These guys are linear transformations. As long as they agree on a basis, they agree everywhere. Okay, so let's look. So what's T sub A of E1? What's T sub A of E1?
E1 if multiplied by the A columns.
So what is that?
Just A1.
It's A1, right? Right? What's TA of E2? going to be A2, right? TA of E3, et cetera, et cetera. So what is this? So TA of EI is going to be AI, right? Right? When you multiply on the right by the ith element of the standard basis, that's just going to pick off the ith column here, right? Okay, what's T of EI? Well, T of EI is AI, remember, right? AI was defined as T of AI, T of EI, right? AI was created to be T of EI, right? That is AI, right? And so these guys agree, right? So they agree on the standard basis, and so they agree everywhere. Okay. So since T and TA agree on a basis, they are equal. Linear transformations that agree on a basis are identical. Okay, so let me give you like an exercise. Let's define a linear transformation from R2 to R2, okay, where L of the vector is going to be, you rotate, no, the flip the across the x-axis, then rotate 90 degrees counterclockwise. Okay, so right, if you give it a vector, it's going to flip it across the x-axis, and then it's going to rotate that thing 90 degrees counterclockwise. Okay, so this is, if this is V, then this thing here is going to be LV. Okay, so what's the matrix? What is A such that L is the same thing as T sub A? Okay, and how to construct it is right here. Turn to a neighbor and talk with them, please. Neighbor or neighbors. Okay. Anybody want to say how to do it or what they're thinking? Kate.
I'm just plugging in the standard basis,
Yep.
so 1, 0, and 0, 1.
Right,
and then
1, 0, here it is. 0, 1, here that is. Let's do 1, 0 first. So what happens to 1, 0? flips across the x-axis, nothing happens. Rotates 90 degrees counterclockwise. Okay, so that becomes 0, 1, right? That's going to be our first column. What about the other guy? Well, flips across the x-axis, rotates 90 degrees counterclockwise. Oh, it becomes 1, 0. Okay. Okay, so this is it. 0, 1, 1, 0 is the matrix that flips and then rotates 90 degrees counterclockwise. And we can check it out on something. I don't know, like 3, 2. What happens to 3, 2? Well, it becomes 2, 3. Right. So does that make sense? You flip it across here, and then you rotate it 90 degrees counterclockwise, right? And that actually just flips the coordinates, right? So yeah, that's right. Okay. I should have chosen a more complicated one. Okay. Okay. So that seems kind of cool, right? Whatever linear transformation you have, you can turn it into a. It actually corresponds to a matrix. Okay, and now we're going to go into the world of abstract vector spaces, so matrix representations of linear transformations from one vector space to another vector space with respect to bases, let me call them B and actually E and F. So E and F of V and W, respectively. Okay, so we're going to need, in order to make a matrix, we're going to need to put coordinates on these guys, right? We're going to need to put coordinates on the vector spaces. So we need bases, right? Once we have bases, we can put coordinate vectors on the vector spaces, right? So we take a basis E of V, we take a basis F of W. That will give us coordinate vector, right? So like E a basis of V, right? That gives us a map. Right, that gives us a map from V to Rn, say V is n-dimensional. And that W is m-dimensional. Okay. If you have a basis of V, well, that'll give you the coordinate vector map. Right? You guys remember the coordinate vector map? Right? It takes a vector, and then it maps it to, a bunch of coefficients, a1 to an. In other words, it takes V to the coefficients that you would use to recover V as a linear combination of the bases. Right. Similarly, we got this map from from W to Rm, right, which would do something similar, right? It will take this guy over here to corresponding coordinates. Right. And remember that these things are isomorphisms. These maps are isomorphisms. They're two-way maps, right? You can go from the coordinates back up to the vector. You can go from the vector to the coordinates, and it's one-to-one and onto. Importantly, it's an isomorphism. Okay. So so really, what we're going to construct, when we say we have a matrix representation, what we're going to construct is this guy. This guy. We're going to construct the matrix A that goes from Rn to Rm in a way that parallels the behavior of T going from V to W. Okay. So, thinking of V as Rn, thinking of W as Rm, what matrix is going to behave like T does on V and W? Right. So that's the idea to construct a matrix A. It's going to be n by n, look at the dimensions, right? Such that TA's behavior from Rn to Rm exactly parallels, or actually exactly mimics that of T from V to W. So let me do a concrete example first. And this will sort of outline the procedure. So yeah, so we're just going to do the differentiation operator. So V is going to be polynomials of degree under 3, W is going to be polynomials of degree under 2, and T from V to W is going to be differentiation. Okay, and then we're just going to use the standard bases. So our basis for V is going to be 1x squared. Our basis for W is going to be 1x. Okay. And we'll get the matrix representation of T with respect to E and F. That's what we're going for. The matrix representation of T with respect to E and F. Okay. So let me draw the picture again. Going from V to W, we've got this thing, and we want this guy down here. This is what we want. Okay. What we have all this stuff, right? We've got the isomorphism from E. We've got the isomorphism from F, right? These are the coordinate vector map guys, right? And what we're saying is that we can fill in this last part here. Okay. Okay. So here's how the construction goes. So what you do is you say you take each element in the basis, you take each element in E, and you run it through T. So you take T of 1, you take T of x, and you take T of x squared. Okay. And then you take the representation of that, take the coordinate vector of that with respect to F. Okay, and those will be the columns of A. This is going to be your A1. This is going to be your A2. This is going to be your A3. Okay, so let's just do that. What's T of 1? When you differentiate 1, you get 0, right? What's 0 represented with respect to the F basis? What's the coefficients of 0 with respect to the F basis? Well, 0 and 0. Right? It's going to be 0 of this plus 0 of that. Right? So vector A is going to be 0, 0. What about vector B? What about A2? It's T of x is 1. What's 1 with respect to the, what's 1's coordinate vector? 1, 0. And what about the last one?
0, 2.
0, 2. Right? So the matrix representation, right? The matrix representation of T with respect to E and F is going to be this matrix, 0, 0, 1, 0, 0, 2. Okay. So now let's see that it does. Let's see what I was talking about when I said it mimics the behavior. Right? That part should have been kind of mysterious. What did I mean by mimics the behavior? Somebody give me a quadratic, whatever quadratic you like. You don't like any quadratics. Okay, I don't know, like 5 plus 2x plus x squared. That's cool. Yeah, I guess there are no likable quadratics. Why? It's like asking for your favorite color or something like that. And like, I don't really have a favorite color. Do people have favorite colors? Do you guys associate fields of study with colors?
Yes.
Is that a thing? So my kids were asking me last night, so what color is science? What color is math? What color is biology? What color is this? And I'm like, brown, green. I don't know. Anyway, yeah. It's like they don't have colors. Okay. Okay, so let me show you what let me show you the sort of the miracle or the magic or whatever. So look, if we run this guy through t, we differentiate, right? And it becomes just 2 plus 2x, right? Okay, but let's run that guy through the coordinate vector. The coordinate vector transformation, right? The associated coordinate vector with respect to the spaces. Well, that's going to be 5, 2, 1, right? That's going to be 5, 2, 1. Now let's hit that guy with A, right? So we get 0, 1, 0, 0, 0, 2, 5, 2, 1. What do we get? Well, we get 2, right? We get 2 and we get 1. Right? We get 2 and 1. Oh no, 2 and 2, excuse me. 2 and 2. Right? Well, what happens when we take this guy and run it through the coordinate vector map for f? Well, it goes down to 2, 2. Okay. And that's going to happen for every single thing you have here. So whatever thing you start off with, if you run it through t and then through the coordinate vector map, or you run it through the coordinate vector map and then hit it with the matrix, you get the same thing. So it's in that sense that this matrix captures everything that the differential operator does. Okay, like whatever quadratic you have, you can differentiate it in this way. Okay, you can take its derivative, right? Just multiply the coordinate vector by this, and then you're going to get the coordinate vector for the answer. Okay. Yeah.
Does it only go that way, or could you go backwards with like an inverse matrix, like an antiderivative?
Oh, well, the thing is that, the antiderivative, it's not going to work because you get constants here, right? You got an arbitrary constant, so it's not, it doesn't, it's not well defined, basically. Yeah. Yeah. Right. There's no good inverse, and that's because this thing has a kernel, right? The kernel being the constants. The constants get killed off,
Yeah.
and so you can't go backwards. Okay. Okay. So now let's run through the why that actually worked, right? This is the thing that should be mysterious, right? How we constructed A, right? This is the part that I just pulled out of a hat. I said, here's how you construct A. Apply t to each of the basis vectors, and then take the coordinate vector with respect to the second basis. Right? That should be like y. Are any of you from southern United States? No? Okay. I was going to say if you said why rather than why. Because I say why. I was born in North Carolina. I would say why. To the mockery of my children. Okay. Okay, so here's the proof, right? Right, so let me, I'm sorry, I think I just erased, no, it's right there. Great. Okay. So let me call, I'm gonna put names on these maps. So I'm gonna call this map P, and I'm gonna call this map Q. Okay, the coordinate vector maps. Okay, this is the coordinate vector map. P takes V to its corresponding coordinates. Q takes W to its corresponding coordinates. Oh, and actually before I get there, I need to do some sort of warm-up question. If E is B1 through Bn, what is P of B1? One, you're close, but you're a little bit off, right? P of B1 should be a coordinate vector, right? So it's got to be, n. It's going to be a whole vector here. So 1, 0, 0, 0, 0, 0, 0, 0, right? It's going to be 1, 0, 0, 0, 0, 0, 0. In other words, it's the standard basis element, the first standard basis element, right? What's P of B2? It's going to be the second standard basis element. P of 3, and P, so P of Bi. Each of those, when you apply P to the standard basis element, you get the when you apply P when you apply the coordinate vector map to the basis elements, then you get the standard basis elements on it. Okay. That's really important. Okay. That's going to be important in the explanation that we give right now. Okay. So, right, so, okay, so actually, here's the theorem. Given a linear transformation from one vector space to another, E being, say, V1 through Vn, F being W1 through Wm, and these guys are bases for V and W, respectively. Then there is a matrix A. Okay, there's a matrix A, an m by n matrix, M, such that A of such that for any vector in B, A of the coordinate vector of E, coordinate vector of V with respect to E is the same thing as the coordinate vector of TV with respect to F. This matrix, this A, is called the matrix representation of T with respect to bases E and F. Okay, so this is sort of like a theorem definition, right? So notice that what we're saying, let me let you guys finish writing. Right faster? I'm joking. Take your time. Okay. Notice that what we're saying is that the matrix should make this diagram commute. So it should make things commute here. Okay. That is, what it's saying is that if you take a vector v and then get its coordinate vector with respect to e, right? So you take a vector v and then you take its coordinate vector with respect to the e basis, and then you hit it with a, right? Then you hit it with a. You get the same thing as if you took the vector and then hit it with t first, right? And you got tv, and then you took the coordinate vector of that with respect to f, right? So you went down this way and you got tv with respect to f. Those two things should be equal, right? That's what, so the matrix representation of the transformation is the matrix that makes this diagram commute. That's the language that it makes the diagram commute. And we've seen this kind of idea before, right? You can either add first and then use the linear transformation, or you can use the linear transformation and then add afterwards, right? Or this sort of thing. Okay, so the matrix, what we're saying is that there's a matrix that makes this diagram commute. So, okay, so I think, yeah, I'll just take a second to construct. So, proof. We construct A. Let AI, the ith row of it, be T vi with respect to f. This is what we were saying over here. This was the mysterious step, right? Like the ith row, the ith column is going to be, you take t of the ith basis element and then represent it with this t of the initial t of the ith element of the basis of the domain space expressed with as a coordinate vector with respect to the basis of the target space. Okay. This thing. Okay, that'll do, and that does it. So now notice now observe. Now observe. If we go through T and then Q, so we go through T and follow that thing with Q. So take, for each v sub I in E, consider T of v sub I, and then hit that thing with Q. Well, that's just going to be T v sub I with respect to f, right? By definition, right? Q is the, sorry if this notation is getting kind of heavy, but Q was this guy, the coordinate vector map. The coordinate vector map with respect to f. So all it does is puts this guy in, gives the coordinate vector with respect to f. Okay. But also, if we consider P of v sub I, and then follow that with T sub A, what do we get? What's P of v sub I? Remember, P is the coordinate vector map with respect to the to the E basis, which was the v sub i's, right? So we're taking the coordinate vector of v sub I with respect to the v sub i's. Well, what's that? P of v sub I is, we just said this a second ago. This was going to be E sub I. Do you remember that? This is what Ava got. You guys remember that? Okay. Right, so this is going to be T sub A, E sub I. Right? Because if you're representing V sub I as a linear combination of the V sub i's, but if you're representing V sub 1 as a linear combination of the V sub i's, well, it's going to be 1 of the first guy and 0 over the rest, et cetera, et cetera. Right? So this is going to be T sub A E sub I, which is just A E sub I. What's A E sub I? Well, A, when you take the matrix and you hit it with the ith element of the standard basis, you pick off AI, exactly. You pick off AI, right? But AI was this, right? Right? That's why we constructed AI in that way. AI is exactly the thing that you get if you'd gone the other way. Okay. So what does this tell you? This tells you that if you go this way and then down, and this way and then across, on the basis, you get the same thing. But since these guys agree on the basis, then they're going to agree everywhere. Okay. So Q composed with T and T sub A composed with P are still linear transformations. We just seen which, as we just saw, agree on the basis E. So they must be the same. QTV equals T sub A PV for all V in B. Right. In other words, T sub B with respect to the F basis is equal to A of B with respect to the E basis for all V. Right. In other words, A is the A that we constructed. That is, the A we constructed is the matrix representation of T with respect to bases E and F. I'm sorry to do this, but let me take 1 minute and run through a quick example. Another example. So we let S be the span of a bunch of functions. E to the x, x e to the x, x squared e to the x. Okay. And then D is going to be, again, the derivative operator. Okay. And we want the matrix. So D goes from S to S, and then we can use the basis, right? This is the basis, let's call it B. Right? We use the basis B to get a coordinate map from there to R3. And we also use it on the other side to get the coordinate map with this to R3. So what's the representation with respect to B and B, so using B on both sides? you would just follow the procedure that we just outlined. You'd say, okay, well, look, here are our basis vectors. So I hit them with I hit them with the linear transformation, and I get, well, this stays the same. I get first derivative second plus the derivative first times the second, and first derivative second plus the derivative first times the second, right? Right, and then I represent those guys with respect to the target basis, target spaces basis. Right, I say, okay, e to the x in terms of this basis is 1, 0, 0. Right, this thing in terms of the basis is going to be what, 1, 1, 0. And this guy with respect to the basis is going to be 0, 2, 1. 0, 2, 1. And so my matrix is 1, 0, 0, 1, 1, 0, 0, 2, 1. Okay. And then you can I'm not going to do it because we're out of time, but you can check that this thing differentiates linear combinations of these guys just like the derivative would. Okay, that was probably the hardest thing we're going to do for a while. So if you understood it, congratulations.